Hey everybody, and welcome back to Calc 3 Online. So I just want to talk a little more about curl and divergence today. There's something we proved in the last video that said we basically showed that the curl of the gradient of f equals 0. And if you think about this, what this is basically saying is that if, like the field in here, capital F is conservative, then the curl of that field is going to be equal to 0, right? Because we know that this is basically what it means to be conservative. And so what we actually typically like in the world is basically a way to figure out if something is conservative, because a lot of nice things like you have here, like if it's conservative, then you get this. There's tons of other things out there where if they're conservative, then something nice is going to happen. And so we like to have a way to test that. And so it's logical to kind of think, well, is the converse of this statement here true? So if the curl of something equals 0, then is it conservative? And it almost is true. But it's another one of these situations where you do need to not have like weird singularities. So basically we saw some fields where it's like undefined at the origin or something like that. And there's other ways, right? You could have a field be undefined at certain spots, but basically if it's defined on all of R3 and the component functions all have continuous partial derivatives, and the curl of the field equals 0, then you get that f is conservative. So basically, if it's a really nice field and it's well defined everywhere, then it's going to be conservative. So it's actually another one where really the thing that needs to happen is it needs to be simply connected. And if it's simply connected, then that's like kind of our property for being in a very nice space. Then it's going to be conservative. And the curl equals 0, then it's going to be conservative. So this one right here, super well defined, no issues, no weird singularities or anything like that. So basically if we can set up our curl, so what I mean by that is this. So this is just my, gradient crossed with f. And so if this thing works out to be 0, then it's going to mean that this field is conservative. So if we go through and just do all that out, right? So we're going to have, the partial of this one, right? So that's going to be like 6x y z squared minus, let's make this a vector here, minus the partial of this one, right, with respect to z. So that is actually also going to be 6x y z squared, which is good so far. And then we have, we're going to blank that out and blank that out. And so we're going to do the partial of this one with respect to x, right? So that's going to be 3y squared z squared. And then minus the partial of this one over here with respect to z, which is also going to be 3y squared z squared. And then last but not least, take the determinant of this little 2 by 2 here. And what you'll see is 2yz cubed minus 2yz cubed. And so if you look at that, right, we literally do get the 0 vector. And so the curl of this thing is equal to 0. It's a well-defined thing. So that is like the necessary condition for the converse of this being true. So now that shows that this thing is conservative. It's a very, very, very handy test. One of the ones that I feel like I probably use the most often in like my higher level math classes and stuff. So I thought it'd be good too to just show another one of these where we basically find lowercase f, so that capital F equals del lowercase f there. And so we've done this before, but it's always good to see another one of these. So what we need again is f to equal y squared z cubed, right? f with respect to x. Sorry, no, I'm doing this all wrong here, sorry. We need f with respect to x to equal y squared z cubed. Then we need f with respect to y to be 2xyz cubed. And then f with respect to z needs to equal 3xy squared z squared. And so just like before, basically we can take this one here and we could integrate with respect to x. So we would just get x y squared z cubed, and then we can have y z functions be going to 0, right? Because like if you went back with the derivative, right, those y z functions would disappear. So there can be some sort of g of y comma z there. And then what we can do is we can take the derivative of this, because this is like my contender for what lowercase f is. So I can take my derivative of that with respect to z and sort of compare it to this, right? So if I take my derivative with respect to z, I'm going to get 2xyz cubed plus g with respect to y. I'm just going to write g with respect to y for a second. And then if you compare these two, right, you can see that this part, the g with respect to y, that derivative, just basically has to be 0, right? So now, right, what it basically means is like my current contender is f of xyz is 2xyz cubed. So this is sort of my current lowercase f function that I have. Oh wait, sorry, I looked at the wrong thing. So what I wanted to say was it could be xy squared z cubed, right? So this was, I took the integral, so this was the lowercase f. And then because this has to be 0, right, this must just be a function of y at most, or sorry, function of z. So call it like, I don't know, h of z or something. So that is what basically it could look like right now. So then we're going to take this thing I just circled over here, right? And if we integrate it take the derivative with respect to z, then we can compare it to this, right? So if we do that, we basically would get 3xy squared z squared plus h prime, and it's just a function of z. And so now if we compare it to this right here, right, you can see that h prime of z must equal 0, right? And that means that basically my function of xyz, this part basically, the only thing that it could be over there is just a constant, right? Because when you take the derivative equals 0. So this is actually the scalar function, lowercase f, that if you took the gradient of, you're going to get this, and that's what it means to be conservative and all that. So those things always take a little bit of time. You got to kind of like keep going back and forth and do a derivative and an integral and derivative and integral and just keep doing that. But that is lowercase f that would work here. All right, so what I want to do now is actually do something where I'm going to rewrite Green's theorem in what we would call this vector form. And actually in my room on my wall, this is actually what I have. And there's actually 2 of these, and I'm going to go through both of them here. So let's do it. So we know from Green's, right, like the line integral for a planar like closed curve like this. This is just another way to write the line integral for a planar closed curve. By Green's, what that equals, right, is this double integral over d of q with respect to x minus p with respect to y, like d8. And for a planar curve, okay, the curl, if you just compute it out, right, so we got I, j, k, and then we got partial with respect to x, partial with respect to y, partial with respect to z, and then we've got p q, and then we don't have anything here because it's planar, right? If you look at this, so when you blank this out, you're going to get 0, right? And then the partial of this with respect to z is also 0. So you get nothing in I, right? And then if you blank this out, right, you get 0. And then p also is not a function of z. So when you when you take the partial of this with respect to z, you also get 0 in j. That's a j. Oops, that's a horrible j. And then if you blank out the last one, though, you'll get q with respect to x, and then you'll get minus p with respect to y, okay? And this is in, like, the k component. That's, like, all that's left. That is the curl of f, right? If it's planar, if it's two-dimensional, right? So then I want you to see that if you take the curl of this kind of f, so a planar one again, and you dot it with k, right? Notice that that would just be, that would be q with respect to x minus p with respect to y in the k component, right? Dotted with k. And we know that, like, when you do, well, here, I'll just write it out. So if you do this out, you get k, so you can pull that constant out. Q x minus py is just like a multiplier there, and so you can just pull that out. And then you have k dotted with k, which is just the magnitude of k squared, but k is a unit vector, and so that whole thing would just simplify to q with respect to x minus p with respect to y, right? And so if you look at it, right, Green's theorem, which is this double integral q with respect to x minus p with respect to y dA, you could actually just simplify it, right, to something in terms of curl. You could do a double integral over d, and then you'd have curl of f, curl of f, right, and that vector dotted with k, and then just dA. So this is actually a very famous identity also. It's another way that we write Green's. And it's just saying that this line integral is the same thing as the curl of the field dotted with k, and then dA. Right? And conceptually what this is saying that the line integral of, like, the tangential direction, so there's a unit tangent direction, along C, right, is the same as the vertical component of the curl of f over the region D enclosed by C. So it relates the this unit tangent with the vertical component of the curl of f, okay? So that's an important thing to kind of know. So this line integral can also be written that way. It can be written this way with Green's, but this is also Green's. It's just what we call a vector form of Green's. So what I'm going to do now is I'm going to do something very similar, but I'm going to look at it in terms of the normal component, okay? So you can do the same kind of arguments, but you're going to see that something else pops up nicely out of this. All right, so R of t, so it's a planar curve, so we have like x of t, y of t, right? And then the unit tangent, right, would just be x prime of t over the magnitude of r prime, and then comma y prime of t over the magnitude of r prime, right? That's just normalizing the vector r of t. And the unit normal, okay, this thing that I'm going to kind of relate to Green's here in a second. So when you have when you have just, two components in a vector, you can easily get the normal if you just literally like flip and negate, right? So what I'm going to call the n of t is just y prime of t over the magnitude of r prime, comma, negative x prime of t over magnitude of r prime. So, this is just, if you literally dot them, right, you would get 0 because you just flip and negate the two of those things, okay? So, so now, like, we know from, like, doing line integrals for a while that if you do f dotted with, I think we first saw it with a unit tangent vector, but if it's the same idea, you just change the vector. So we're doing f dotted with a normal vector, unit normal, ds. This is going to be equal to the integral from, like, we'll just say a to b, and then f dotted with n, like of t, times the magnitude of r prime of t dt, all right? So if we just go and we're just going to pop in that dot product now. So we have basically, we're still thinking of f as just like pq, it's just planar. So we're going to have a to b, and then we're going to have p y prime of t over magnitude of r prime. So that's just, this times p, that's in here. And then we're going to have minus q x prime of t over magnitude r prime. And then again, we're just going to multiply all this stuff by magnitude of r prime dt. Okay, so now what this is saying, if I multiply that in, right, I'll kill off the r prime. And so I get p r prime of t minus q x prime of t dt, right? And if you think about what that's saying, right, so in, this r prime right here, you really have like dy dt, right, and this is dx dt. And so if you're multiplying this thing by, this whole thing has a dt that is multiplied by right there, then the dt's would go away, right? So maybe I should I'll rewrite y prime for a second here. So so we have dy dt, and then we're canceling the dt's, right? And I could do the same thing in here with x prime. And so what I then get is p dy minus q dx, right? And if you think about it, in terms of greens, you can do one last step and simplify this thing and get something actually that's meaningful with divergence, actually. So what I'm going to do is, so if you think back to greens, what we say is we typically write the dx, then the dy. So what I'm going to do is I'm just going to rewrite this as integral from a to b minus q dx plus p dy, right? And then I'm literally just going to use greens on this thing, okay? And so greens says that if you have p dx, q dy, you take the x partial of this thing, and you take the y partial minus y partial of that, right? So if you look at that, right, you take p, because that's the thing over here, and you take the x derivative of that. So we're going to get, so this is me playing greens now. So this is going to be double integral, p with respect to x, and then I'm going to do minus this negative, so I'm going to get a plus, the derivative of this with respect to y. So really double negative, q with respect to y, right, dA. But here's the kicker. The thing I have right in here, right, if I do partial of p with respect to x plus partial of q with respect to y, that is truly just divergence, right? So this is just divergence of f of xy dA. And so, long story short, I can take this line integral and I can write it that way, right? And what this is actually saying is that this is basically doing Green's theorem, but looking at the normal component as you go around. And it turns out that it involves divergence, which probably shouldn't be super surprising because we're literally talking about the stuff that's leaving the double integral surface or region D there, right? We're just talking about this stuff that leaves D. And this actually has a name, and we will talk about it in higher dimensions as well eventually, but this is something called flux. So flux is kind of a measurement of how much stuff leaves a closed surface like this, or closed loop. But you can do, this is flux in 2D, but you can also talk about flux in 3D also. So this is an important vector form of Green's also, and it relates the normal component to the divergence. All right, so I want to do one more problem. So using what we just showed here, okay, I want to prove this messy thing. All right, so if we're going to prove that this thing equals this thing using Green's theorem there, what I'm going to do is I'm basically going to start with this side, and I'm going to show just applying basically this Green's theorem when you do f dotted with n. And I'm going to rewrite this with a divergence, and then show that actually this all cancels out to this. So this is the kind of stuff too that I took I think I took 2 college physics courses, and if you like problems like this is basically what I remember doing in my physics college courses. A lot of it is just like deriving different identities and theorems and things from vector calculus. It's basically what a lot of college physics looks like. So let's do this. So I'm going to take this and I'm going to apply Green's theorem. And so this part right here could basically be rewritten as the double integral of d, divergence, and then, this right here, right there, is like my f over here. And so it's going to be the same as the divergence of, lowercase f times del g, yes, and then dA, right? And so then what I'm going to have to do is I'm going to have to simplify what this thing is, okay? So what I'm actually going to do is I'm going to just take the inside here, and I'm going to simplify that down. So divergence of f times del g is literally, I'm just going to do the divergence. So I'm just going to compute the partial of, with respect to x, of f times, I might as well just do this, and I can do this step too. So I'm going to, the gradient of g is just going to be partial of g with respect to x, right? And then plus, this is the divergence plus, right? It's just like the dot product. Partial with respect to y of f times partial with respect to g with respect to y. Basically, I should probably put some parentheses in here. If I was going to do the partial of this with respect to x and this with respect to y, I would need to do like chain rule. So I'm going to just do the first function times the derivative of this with respect to x. So that's going to be partial squared g over partial of x squared. And then times the derivative of f with respect to x times the second function, which is just g with respect to x. Then do the chain rule in the second term, and you would get f partial squared g partial y squared plus partial of f with respect to y times partial g with respect to y. Okay. So what I can do now is I got some stuff I could factor. So I could pull an f out of here, and I would have partial squared g over partial x squared plus partial squared g partial y squared. And then I think I'm just going to write this down. I'm just going to copy that over. And if you look at this, so this part right here is partial squared, oh wait, that's an x, sorry, of g with respect to x, the second partial of g with respect to x plus second partial of g with respect to y So that is basically the same thing as just saying f times gradient squared of g, right? It's like just del squared. That's all it is. And this part over here is, you could understand that as a dot product of the gradient of f, right, dotted with the gradient of g, right? That would be the same thing as this. And so what I can do is I can go back to this double integral, and I can write that thing as f del squared g dA plus double integral d of del f dotted with del g dA. And so what I did is I basically, it was a sum, and so if I'm doing a double integral of a sum, I can just split my double integral up over each part. And so all I've just done is so far I showed that this first line integral over that closed loop is the same as these two double integrals right here. So then, if you look though, I had in this thing, I was minusing a double integral over d, del f dotted with del g dA. And so this is where the nice stuff cancels, because this whole part and this whole part cancel. And what this whole thing up here simplifies to is just this part. It equals double integral of d f times del squared g dA. And that is what we wanted to show that it equals. And so that proves it. Basically, if you want to prove these identities, you just manipulate one side of it, and you just, if you start with the right side and you get to the left, you've shown it. If you started with the left and you get to the right, you've also done it. But typically in these things, when I would prove these identities, I would start with the more complicated side, and I would unpack and simplify as I go, and hopefully it simplifies to the nicer side over here. So I just want to show that because that reminds me a lot of stuff I used to do in college physics courses, and just basically symbol manipulation and using Green's theorem and divergence definitions and chain rule and all sorts of good stuff. So there you go.